Here we discuss the solution of a problem from complex analysis. And the problem is on the zeros of an analytic function. And this question has appeared in a CSIR-UGC National Eligibility Test held on 26th November 2020. It is from the section C and it carries 4.75 marks. The problem is for z not equal to minus I, let f of z is equal to e power 1 by z plus I minus 1. Which of the following are true? So note down, are true. Option 1, f has finitely many zeros. Option 2, f has a sequence of zeros that converge to a removable singularity of f. Option 3, f has a sequence of zeros that converge to a pole of f. Option 4, f has a sequence of zeros that converge to an essential singularity of f. Solution. We have f of z is equal to e power 1 by z plus I minus 1, where z not equal to minus I. Notice that the function f of z is analytic everywhere except at z is equal to minus I. Now, z is equal to minus I is an isolated singularity of fz because it is the only one singularity of fz. Therefore, we can have the Lorentz expansion of fz about z is equal to minus I. And it is given by e power 1 by z plus I minus 1 is equal to 1 plus 1 by z plus I plus 1 by 2 factorial into z plus I whole square in the denominator plus etc. minus 1. Plus 1 minus 1 cancels and you are left with 1 by z plus I plus 1 by 2 factorial z plus I whole square in the denominator plus so on and so forth. We have seen in the last slide the Lorentz expansion of fz is this one. And notice that the negative powers of the part consisting of the negative powers of z plus I is called the principal part of the Lorentz expansion of the function f of z. If the principal part has no terms, then z is equal to minus I is a removable singularity. If the principal part has finitely many terms, then z is equal to minus I is a pole. And if the principal part has infinitely many negative powers of z plus I, then z is equal to minus I is an essential singularity. Here we notice that the principal part has infinitely many inverse powers of z plus I. Therefore, z is equal to minus I is an isolated essential singularity of fz. Hence, it is neither a removable singularity nor a pole. We now discuss the zeros of the function fz, that is equal to e power 1 by z plus I minus 1, and the zeros are given by e power 1 by z plus I minus 1 is equal to 0 will imply e power 1 by z plus I is equal to 1, and 1 can be written as e power 0 plus 2n pi I, n belongs to z. This is the general value, and that will be equating 1 by z plus I is equal to 2n pi I, z plus I is equal to 1 by 2n pi I. Push this I to the other side, then you will get a sequence of zeros zn is equal to 1 by 2n pi I minus 1, n belongs to z. We have a sequence of zeros. How many zeros are there? There are infinitely many zeros are there. This shows that fz has infinite number of zeros, and our option 1 says f has finitely many zeros. Therefore, the option 1 is not true. Now let's discuss the convergence of the zeros. We have Zn is equal to 1 by 2n pi I minus I. Limit n tends to infinity of Zn is equal to limit n tends to infinity of 1 by 2n pi I minus I. 1 by n limit n tends to infinity will be 0. That will be minus I. Thus, f of z has a sequence z and n is equal to 1 to infinity of zeros that will converge to minus I, which is an essential singularity of fz. Let's look at our options. Option 2 says f has a sequence of zeros that converge to a removable singularity of f, which is not true. 3. Option 3, f has a sequence of zeros that converge to a pole of f, which is not true. The fourth one says f has a sequence of zeros that converge to an essential singularity of f. That is right. Therefore, the option 4 is true and the options 2 and 3 are not true because z is equal to minus I is neither a removable singularity nor a pole. So therefore, our answer is option 4. So that is the discussion of the solution of a problem on the sequence of zeros from the complex analysis. I wish you all the best. Thank you.